Kia ora and welcome to this video on question 4 of the 2022 School Calc exam. There's 3 parts to this question. The first is a link between complex numbers and a nasty trig identity, which actually has appeared in a past scholarship exam. Part B is def by trig identity. The integral, at least the way I've done it, involves some serious trig. And then part C is a conics question, which again brings in trig. Okay, first part, we're introduced to an expression for cosine theta in terms of Euler's number. We don't need to prove that first part. Let's go cos theta is e to the I theta plus e to the minus I theta all over 2, and we want to power that by 6. So if I take cos to the power of 6, it's going to be all of this thing to the power of 6. 1 over 2 to the 6 is 1 over 64. And then we want to take the numerator and power it by 6. Using the binomial theorem, we get the first thing to the power of 6. Then the coefficients, we need Pascal's triangle. There are our coefficients that we want, 1, 6, 15, 20, 15, 6, 1. So the next term is 6 lots of the first thing to the power of 5 times the second thing, 15, first thing to the power of 4 times the second thing squared, etc. I'm going to save a little bit of time here because I'm going to spot a pattern. The first term, using power rules, is e to the I times 6 theta. The second term, when we see that it's e to the I 5 theta there, and then e to the minus I theta, if we add those powers, we get e to the 4 theta, e to the I 4 theta. And then the next one is 15 lots of e to the I 2 theta. And the middle term is 20 because we get a cubed for the first and a cubed for the second, so the e to the I thetas multiply to 1. And then we get 15 e to the minus I 2 theta, the powers are dropping by 2's. 6 e to the I times minus 4 theta. And e to the minus I 6 theta. Then we group them by putting the first two terms together, the first term and the last term together as one, and then e to the I 4 theta, e to the minus I 4 theta, and e to the I 2 theta, e to the minus I 2 theta. And the reason for that is if we look back at the formula we're given, if we change theta to n theta, that's our relationship. So if I split the 64 into 32 and then bring a division by 2 into the brackets, and then we've got 6 over 64, which is the same as 3 over 32, but we also need the need the 6 there. We've got 15 e to the I 2 theta plus e to the minus I 2 theta. and then the last term is a 20. We can then use the relationship in red, because this whole thing here is cos of 6 theta. So we get 1 over 32 cos 6 theta. Second term there, this whole dude with the 2 is cos 4 theta. And we get 15 cos 2 theta plus 20. And that's the proof. Gee, 20 over 32, yeah, 5 over 16. Oh, my bad. No, it's that needs an over 2 there. So I paused because I looked wrong. It was wrong. So it's 10 over 32, which is 5 over 16. Okay, done. It is possible with this to actually work on the right-hand side and reduce the cos 6 theta, reduce the cos theta, and reduce the cos 2 theta, all down into thetas using trig identities, but it's really, really intense and takes a lot more time than the binomial expansion I just did. Okay, the asteroid shown is defined by the parametric equations. The given parametric equations to make the integration supposedly easier. But if we just look at, say, this symmetry, and if I try find this area here, how do we normally find area? We integrate y with respect to x. Okay, so we're integrating y, which is sine cubed, and then we need a dx, but we need to replace the dx with dt if we're going to integrate with respect to t. So we go x is cos t all cubed, dx dt, 3 cos squared times minus sine. So our dx bit that we replace is going to be 3 cos squared t times minus sine t dt. And the other thing we need to change is our limits, because this dude here is x equals 0, the left boundary, and this dude's x equals 1. But x equals 1 actually corresponds to t equals 0, it's an angle, and x equals 0 corresponds to t equals pi over 2. And you can find that out by just making x equals 1. If you make x equals 1 in the equation, you can see that t is equal to 0. And when you make x equal to 0, t is equal to pi over 2. Okay, so our limits actually look a bit funny, but we have our bottom limit being pi over 2 and our top limit being 0. And that's the integral we need to find. One small catch is that we need to also times that by 4, because I'm just finding the area in the first quadrant using symmetry, multiply it by 4. So this is the integral that we actually need to find. The setup itself wasn't too nasty. We were just using the hint, the parametric form for the hint. Okay, but the integration itself is a mess. I can flip the limits back around if you're not happy with the fact that the top limit's lower than the bottom. We have a minus in the integrand, so if we want to get rid of that minus, we just flip the limits around, integrate it backwards. We've also got a 3 there, which I can pull out the front as a 12. So if I go 12, flip the limits back around, get rid of the minus, I've got sine to the 4 times cos squared. And I need to integrate this using some sort of identity or substitution. Now, there's a couple of ways you can attack this. I think the easiest way to do it is to replace the cos squared with 1 minus sine squared. And that means you're integrating sine to the 4 minus sine to the 6. And I think part A was a bit of a hint to us because we just found an identity for cos to the 6. So if we just find an equivalent identity for sine to the 6 and sine to the 4, then we'll be able to integrate it. So let's go back to, okay, sine theta there, e to the I theta minus e to the minus I theta over 2i. And we want to power this by 6 and also power it by 4. Um, 2i to the power of 6 is negative 64, so we get negative 1 over 64. And then we get the same stuff as before, we're just got to be careful with signs here. So we get e to the I6 theta plus, what were my coefficients before? It was 6, 15 and 20. It's going to alternate between pluses and minuses, depending on whether I take an odd or an even number of the second term. The second term here has got a negative in it. Okay, so that's expanded, and group the terms together again like we did with the first identity. Okay, and then I need to distribute the 64 again, so I'll make that 32, divide all that by 2, divide that by 2, divide that by 2, and divide that by 2. So I've got minus 1 over 32 cos 6 theta minus 6 cos 4 theta plus 15 cos 2 theta minus 10. I need a similar one for sine to the 4 theta. This is definitely one of the harder questions in this exam. 2i to the 4 is just 16. So we've got 1 over 16. We've got the first term to the power of 4. Coefficients for a power of 4 is 1, 4, 6, 4, 1. distribute the 1 over 16 to an eighth. Okay, if you make a graph on Desmos and you graph sine to the 6x, so let's have a look at this. So I graph, this is just checking that I've got the right expression. You can do this on your graphics calculator and it saves you making an error in the exam. And then I graph my expression for just to check that I've got the right function. Should have prepared this earlier. It's very tedious. Cool, they match. And then do the same thing for sine to the 4. So we get rid of that. Sine to the 4, coefficient 1/8. Cos to the 4, minus 4, cos 2x plus 3. Perfect. Okay, so my identities there match, which means I can then go ahead with the integration. I want to integrate this dude. No, let's just drag it over. Okay. So I've got equals 12, integral. Look, I'm not going to integrate all this stuff because the beauty of the limits that we've got, 0 and pi over 2, and all these trig functions, is when we anti-diff them, they're all going to go to sines. So that's one of them. So I should be using t's. And then the other term is sine to the 4 minus sine to the 6. So minus 1/8. Okay, integrating that with respect to t. When we anti-diff all these cosines, they're going to go back to sines of even multiples. And sines of even multiples, when we've got limits of pi over 2 and 0, are going to all go to 0. So if you want to do the integration, sure, but you're going to be subbing in a whole heap of times to get zeros. So the only thing that's actually relevant is the 10 over 32 times t, when we anti-diff it, and the minus 3 over 8 times t plus sine stuff. Okay, I'm just going to save that. I don't need to actually integrate that, which goes to 0. So our answer to the problem is 10 over 32 minus 3/8 all times pi over 2 times 12. Why is my answer coming out as negative? I got negative 3 pi over 8. Should not be negative. sine to the 4. Oh, my bad, it was sine to the 4 minus sine to the 6, and I did sine to the... Okay, I needed to... that one a plus, that one a minus. So plus, cool, minus there, plus there, minus there, plus there, 3 pi over 8. Cool, which seems plausible, because if you go back to the problem and look at that sort of wedge that I drew, if you just make it a triangle, or even a triangle this way, right? And the base of that's 2 and the height of that's 1, so half base times height gives you an area of 1. Double it for the top and the bottom. Our area should be about 2. And if we look at 3 pi over 8, as a decimal, it's 1.178. So less than 2 as we expect. Okay, hard question. Third part. We've got an ellipse, and we're any point P on this ellipse, apparently the area of the triangle is b squared tan theta over 2. So it's not acceptable just to consider a trivial case, but if we look at P right up the top there, this triangle has a height of b and has a base of 2c, and that angle there is theta, right? So if I split it in half, because I've made an isosceles triangle, then that side's C, that's B, and the angle there is theta over 2. Tan of theta over 2 is equal to C over B. The area of the triangle is a half times 2C times B, half base times height, which is equal to C times B. But C is equal to B times tan theta. So we've got B times tan theta, so tan theta over 2 times another B, B squared, tan theta over 2. So it works for a trivial position, but we've got to prove that it works for all positions of P. Okay. There is a really tedious way of solving this problem, which involves 2 right-angled triangles there, and finding splitting this angle theta into alpha and beta and using the compound angle formula. I'm not going to do it that way, because I found a neater way to do it. I'm going to call this length here u and this length v, and I'm going to use the cosine rule, because I know that this length here is 2c, and I can connect all the sides and the angles together by using the cosine rule. So I've got 2c all squared equals u squared plus v squared minus 2uv cos theta. I also know for an ellipse that the u and the v add together to make 2a always. And if I square this equation, I get u squared plus v squared plus 2uv equals 4a squared. And that enables me to replace the 2uv. So the cosine rule equation becomes 4c squared is, do I want to replace the uv or the u squared plus v squared? I'm going to replace the u squared plus v squared term. So if I replace this u squared plus v squared, it's going to be 4a squared minus 2uv minus another 2uv cos theta. Okay, if I rearrange this, I can get cos theta as the subject of it. Actually, first There's another thing about the ellipse that I know. I know that c squared plus b squared equals a squared for an ellipse. It's on the formula sheet. And therefore, c squared minus a squared equals b squared. Okay, that's how I get rid of the a's and the c's in this equation. Because 4c squared minus 4a squared is 4b squared. And there I've got 4c squared. If I move the a squared to the other side, I've got 4c squared minus 4a squared. So I've got 4b squared is equal to minus 2uv times 1 plus cos theta. Okay, where am I actually going with this? Well, the area of a triangle, if I use half base times height, I've run into a bit of problems because I don't know the height of that triangle. But if I use the half AB sine C rule, I've got the two sides U and V in there. Okay, so let's drag all this stuff down. Need a bit more space for this. Okay, so we were at a stage where we had this relationship here between the two sides u and v, the angle theta, and the side, the value b for the ellipse. Now the area of the triangle is a half AB sine C, so half UV sine theta, and UV can be found using this relationship. So we've got a half (4b squared) over minus 2 1 plus cos theta times sine theta. Okay, I can see there I've got my minus b squared. Why is there a minus? Should there be a minus? Oh, that's terrible rearranging. C squared minus A squared is negative B squared. So negative 4B squared. Negative 4B squared there. Right, that's better. It's a positive now. We've got negative 4 divided by negative 4. So we've got that coming down to sine theta over 1 plus cos theta with a B squared. And then I've seen an identity like this before. We're trying to get it to be tan theta over 2. So we use the double angle formulas for sine. Sine 2 theta is 2 sine theta cos theta. But we can half the angle on the left-hand side and half the angle on the right-hand side. And we can do the same thing for the double angle formula for cos. So cosine 2 theta is equal to 2 cos squared theta minus 1. And then if we half the angle on the left-hand side, we half the angle on the right-hand side. And we need the minus 1 on the other side of the equation. Cos theta plus 1 is 2 cos squared theta over 2. So we use those both those relationships there. Sine theta, 2 sine theta over 2 cos theta over 2. 1 plus cos theta is 2 cos squared theta over 2. We can cancel the cos theta over 2 with 1 down there. And we have cancel the 2's as well. And we've got sine theta over 2 divided by cos theta over 2, which is tan theta over 2 times b squared. And that, my friends, is the proof. So we put a box, smiley face, and that becomes the end of the video. An extremely long one, because that is the hardest question in this exam. Catch you in question 5.